Hello, good evening. Anyone has any questions? Can you hear me okay? Good evening. Okay, thank you. Just want to make sure you can hear me. All right, great. So, no questions? All right, thank you very much. Okay, so today we're going to talk about the volumes. You know, think about in life, right? There's some irregular object. We won't be able to find its volume by the geometry, you know, we have learned. So we're going to use calculus to find the volumes of an, you know, irregular object. The same process, you know, we're going to put this object on. Oh, it doesn't show here. Let me choose again. It doesn't share this right screen. Okay, yes, now it's right one. So we're going to use the same idea. Okay, we're going to slice it, you know, like slicing method. But this is a 3-dimension, right? And we think about to calculate, to approximate this irregular object into sum of volumes of rectangle prisms. So that's easy, right? To find the volume of a rectangle prism, we just do width times height times length, right? Then, you know, we slice it into n many pieces. Then again, let n run into infinity. So but run into infinity, take a limit of that. We call it integral. So it's still the same idea. The idea is this. Okay, we're finding an irregular object, but approximate the volumes of each rectangle prisms, just like this. So each one, so 4 slices here, or 3 slices here. So each one we calculate by, you know, width times height times length. Right, so each of this is width times, just want to show, yeah, right here, right? So rectangle prisms, the volume. And sometimes we do the volumes of if it's a sphere, right? If it's a sphere, we have this, we have volume of 4/3 pi r cubed. If it's a cone, we have 1/3 pi r square h. Right? So find the volume of this subject, we can think to add up all the areas of this semicircle, right? What's the area of a semicircle? Just half of pi r square, right? How do we find the pi r square? How do we find the radius? The radius in this case, just the function value, right? F of x. So we'll talk more about that, but that's the idea. So the definition is this. So the volume of such object equals the limit, add up all the volumes of each rectangle prism, the n pieces, then let n run into infinity. That means we cut into infinite many pieces. So the definition is integration from a to b. Right? We always work within an interval from a to b. Then the area, our area, see the integral is a little different now. Before we're finding area under a function. So the function is one dimension, right? So f of x before is one dimension. So with the second dimension, which is cut into many pieces, so we got a two-dimension units. But now we get three-dimension units because we have area as integrand. We cut x-axis into infinite many pieces, so that's the dimension. So we have three-dimension quantity. Let's see this one. Problem-solving strategy. Finding volumes by slicing method. So examine the solid and determine the shape of a cross-section of the solid. Sometimes it could be rectangle, sometimes it could be semicircle, sometimes it could be something else, like a triangle. It's often helpful to draw a picture if one is not provided. Yeah, picture always helps. Determine a formula for the area of the cross-section. Then 3, integrate the area formula over the appropriate interval to get the volume. So 3 steps, right? 3 steps. Let's see this example. Deriving the formula for the volume of a pyramid. So I think we did very quickly last time. Let's just review this. We know from geometry the formula for the volume of a pyramid is V equals 1/3 of A times H, right? A is the base area, is the area of the base. H is the height. If the pyramid has a square base, then it becomes 1/3 of A square H, right? So if the base is square, it's just we have the base, the area of the base is just A square, where A denotes the length of one side of the base. We were going to use the slicing method to derive this formula. We're thinking about the section, so if we cut, right, if we cut this way, we see the section just a square, just A square. So we see that's H, right? And the height is H. So basically we're putting a pyramid, you know, on the coordinates this way. So what do we need? We need, so H we know, usually H we know, right? From 0 to H. So we want to find, so we see this, if we put in the pyramid this way, we see, when we slice it, we see similar triangles. So we can find a relation between S and A, right? Because why do we need to find S? Because we need to estimate each square. So at S, you know, at X, we want to find is related to A. So in the end, we don't want to get a function in terms of S. We want to get a function in terms of A and H. A and H. Provide, you know, we know A and H. So this way, so we just want to find the value of S in terms of A and H. So we can, you know, similar triangles have corresponding sides in the same ratio, being proportional. So S divides A equals to X divides H. So X is this. So that means we can rewrite this ratio as S equals to A times X divided by H, right? In this way, we can substitute S later on. So the area at any point of value of X, right? The area, just to see this area of this, right? Because we want to calculate the area of each section, which is a square, area of a square in each section, then add them up. So S equals to AX divided by H. So the area of the base equals S square. So that's AX divided by H square. Then we just set into the integral, right? We just add up all those infinite many squares, the area of the squares from 0 to H, the interval from 0 to H. So we set up an integral, lower limit 0, higher limit, upper limit is H. area of the square. Area of square is this ax divided by h square. We simplify a and h, we're treating as numbers. Only x is the variable. So we just get x squared as integrand. Then we integrate this, we'll anti-differentiate this. So we'll get 1/3 of x cubed. Well, from 0 to h, right? Substitute 0, get nothing. Substitute h, we get 1/3 of h cubed times a squared h squared divided by h squared. So you see, we get the formula, 1/3 of a squared equals h. Right? This is just for fun. This one is just for fun. Because this one we can, we can find a volume of a pyramid through geometry. We don't really need to do this. But this shows the geometry, any formula of geometry, the volume of a regular object we can find through geometry. We can also find through calculus. Similarly for this, for the volume of a cone. Okay, solids of revolution. Let's see this one. If a region in the plane is revolved around a line in that plane. Okay, what does this mean? So this means, I'm sorry, just hold on 1 second. This is might be emergency. Hello? 哎，你不能给我打电话，我现在上课，待会儿吧。Okay, sorry, very sorry. That's my friend. Usually is. Okay, anyway, she has a very sad story, so I have to pick up her phone. All right. So let's see like a vase, right? Think about something. Think about an irregular object. All right, you want to find its volume. So what do we do? So if there is a symmetry with the object, we can think this way. We can put the object, on the coordinates, and think about the section of it. Think about the one section of it. Can you imagine this as a vase, right? The section put on the XY plane, and think about the object as the section revolve over x-axis or sometimes over y-axis, right? When we revolve, that means we turn around 360 degrees. We will get 3D object. So let's see this one. So if we revolve this, right? Revolve this what do you call it? The section of this. Okay. If I confuse you anytime, any minute, let me know. Okay. So this is a section of the object. Section means we cut through, right? We cut through the object. And then when we revolve around x-axis, we get a 3D, we get this object. We won't be able to find a volume, through geometry, right? But now we can find the volume of this through calculus. Let's see this example. Using the slicing method to find the volume of a solid of revolution. So we have a function f of x, a quadratic function, right? So we have upward parabola, and we want to find the volume of this one. We want to find the volume of the solid of revolution bounded by the graphs of this upward parabola from 1 to 4. And we want to rotate that piece. Just imagine you have this upward parabola, right? And from 1 to 4, this is a part of this parabola. And we want to rotate this piece about the x-axis, right? About x-axis. So we get a 3D object. So this is the function, right, of f(x), upward parabola. when we have the function, so the area under this from 1 to 4, so we get this shaded region. We get this shaded region. So when we revolve this piece, when we rotate this piece with x-axis, you see we make a 360 degree, right? So the section now, the section we cut this, how do we call it? We cut this vertically. We cut through vertically. So each section will be a circle, right? Will be a circle. So we can find the area of each circle, then add them up. Yeah, that's this piece, right? So we'll have the piece of region under f of x, right? That's just an area, right? The area under the function. Now, when we rotate over x-axis, use your finger, rotate 360 degree. So you're making a circle. You're making a circle. So we have this 3D object. So how do we find the volume of this 3D object? We will use the definition I showed you before, right? We're finding the area of each circle because the section is a circle. So we're going to find the area of each circle. Then add up all those infinite many pieces of circle, the area of the circle. So we're cutting from 1 to 4 into infinite many pieces, right? At each section, at each x value, we can calculate the area of the circle, which is a section. Then we add up these infinite many areas. So that's the idea. Okay, so what's the area of a circle? It's pi r squared, right? So the difficult part is just finding the radius, finding the r. Let's come back to this. So we see the radius for this circle is just the function value at 4, right? So this is red line, right? So that would be the area of this circle when x equals to 4. Well, when x equals to any number, right, from 1 to 4, that's just f of x. We see the r, the radius, just f of x, right? Just f of x. So in this case, we just substitute r into f of x, right? So we have pi f of x squared. And what's the f of x? That's a parabola, x squared minus 4x plus 5. So this will be our integrand. So now, our upper limit is 4, lower limit is 1. Our integrand is just the area of the circle with the pi f of x squared, which is just this upward parabola, right? Dx. And then pi is a constant we can pull up front, and this square we can extend. Then we get a polynomial, right? We get a polynomial of degree 4. The integrand is a polynomial of degree 4. We just use power rule for anti-differentiation. Then we just evaluate from 1 to 4. In the end, we get 78 over 5 pi. And the units is a cube, because this is a 3-dimension quantity. All right, anyone has any questions so far? Okay, great. Okay, no. All right, thank you. Okay, let's see this one. So I want to use the slicing method for this. So f of x equals 1 over x. So we want to rotate the region with x-axis over the interval 1 to 2, right? We know 1 over x graph is one piece is this, because from 1 to 2, it's 1 over x. We have 2 branches, right? One in the first quadrant and one down on the third quadrant. But because the interval is from 1 to 2, so we don't care about the other branch. So we have this piece, we have this region, right? We have this area under f of x. Then we can rotate with x-axis. So this one is very similar from the previous one. We just do pi r square. We set up an integral, lower limit 1, upper limit 2, dx. We're cutting from 1 to 2, cut infinite many pieces. Then pi r square, r just again is our f of x square. So very similar. Okay, so slicing method is very intuitive, right? So another method is called the disk method, because sometimes, so those objects, we can use one function, right, to solve the problem. But sometimes we need 2 functions. We need 2 functions to form the section of the object. Okay, not yet. So now let's introduce a disk method. So this is another method of finding the volume. Okay, let's see this one. When we use the slicing method with the solids of revolution, it's often called the disk method because for solids of revolution, the slice is used to approximate the volume of a solid or disks. To see this, consider the solid of revolution generated by revolving the region between the graphs of function of this f of x, quadratic function again, right? And so this, if you remember, this is called vertex form. So the vertex of this function is at negative 1, 1, and the axis over the interval negative 1 to 3 around the x-axis. So the graph of the function and the representative disk are shown below. The region of revolution and the resulting solid, and so this one. So if we want to find from negative 1 to 2 or to 3, negative 1 to 3. So negative 1, imagine negative 1 up to 3. So this is showing we want to use, so it's just a 2 dimension, right? It's showing here. And then when we revolve with x-axis, we get this 3 dimension stuff. The area under the curve from negative 1 to 3 looks like this. Revolve with x-axis, so we get this 3D object. So still same thing, the volume equals to cutting x-axis from A to B into infinite many pieces. From this case, from negative 1 to 3, cutting into infinite many pieces. That's the integration dx. Then in the middle of the integrand, just the area of the disk. So the only difference with the disk method is that we know the formula for the cross-sectional area ahead of time. It is the area of a circle. So this gives the, so let's see this one. The disk method. Let f of x be continuous and non-negative. Define R, the region, bounded above the graph of f of x. Below by the x-axis. Oh, I think this is a typo. This is a typo. Okay, bounded. Below and above should be switched, right? Should be below the graph f of x, above by x-axis. Like this one. Below the function, above x-axis. So that's a typo. On the left by the line x equals a, on the right by the line x equals b. So lower limit is a, upper limit is b. Then the volume of solid revolution formed by revolving the region around the x-axis is given by this. pi r squared. So this typical one, yeah, because the section, you know, when we rotate over x-axis, over y-axis, or over any other line, it will be, so the section will be a perfect circle. So that's why, so for that, we call this disk method. So you only use the disk method when the cross-sections areas form a, yes, exactly, yes. Yes, rotate with x-axis also we use for y-axis. So we can rotate the piece of region over x-axis, right? And the section will be a perfect circle. And also we can rotate it with y-axis, or we may rotate with any other vertical line or horizontal line you will see in the future. All right. So the disk method just means, yes, you are exactly right. The section is a perfect circle. When we rotate anything, the section is a perfect circle. So that's the formula, pi r squared. And r is f of x for rotating over x-axis. Okay. So for the typical one, we can do that, right? The function is just x minus 1 squared plus 1. We substitute in, the rest is just calculation. All right, again, the answer is 412 over 15 pi, which is a 3-dimension quantity. So let's see this example. Using the disk method to find the volume of solid revolution 1. So by rotating the region between the graph of f of x equals square root of x with over x-axis and in the interval 1 to 4 around the x. Okay, let's see. So square root of x is this graph, right? Because the domain is, you know, 0 to infinity, right? So we just get this. So that's this graph. So from 1 to 4, we get this region. So we get this region. So when we rotate with over x-axis, we get this 3D object. 3D object. We just do pi r squared, right? And r is just function value f of x squared. Then anti-differentiate, the rest is just calculations. We get 15 over 2 pi unit cube, right? 3-dimension quantity again. Okay, I'd like to try this one. I give you 5 minutes. Everyone try this one, 2.8, right? So now the function given is the square root of 4 minus x, and the interval is from 0 to 4, right? So the domain of x we see is from negative infinity up to 4, right? Up to 4. So here we want to find the object of rotating this piece from 0 to 4 over x-axis. Okay, try this. Okay, that's quick. Yes. Okay. Okay. All right. Any different answers? Good. Yeah, I got an A pi also. Anyone didn't get an A pi? Anyone has any question? Okay, great. All right. So James, so no matter what graph it is, you just have to plug into pi r square, right? Well, James, try to understand, because we're going to talk about many cases. We're going to talk about rotate the one piece of region over y-axis also, all right? So don't think this is the only formula to find the volumes. No, we have many more to talk about. So just think about in here, you see clearly when we rotate, so we have to understand the idea, all right? So this is important. And what's more important is this. Thank you. Okay, this is the most important one here. When it says use disk method, you can assume it's pi r squared though. Yes, yeah. If it's talking about disk method, yes, that means the area. That means in here, the integrand a of x is an area of a circle. Okay, so this is most important because we're going to talk about some other methods as well. So imagine the idea comes from this. So sometimes we're cutting x-axis into infinite many pieces, but sometimes it's more convenient to cut y-axis into infinite many pieces. So the r will be different, right? But starting from this point, the integrand is area. It could be area of a square, area of rectangle, area of a triangle, area of a circle, area of quarter circle, area of ellipse, right? So this could be area of anything. So this is just one typical case. For disk method, it's just one of the methods. It's just one typical case. So this is just one typical case. So where is this case survive? This is when the radius is the function value, which means when we rotate the piece of region over x-axis, all right. Okay, let's keep going. Let's see this one, if this one is different. Oh, this one talked about already. All right, so that's over. Okay, great. A pi, yes. Okay, now you see, now we want to rotate the piece over y-axis. Let me skip this formula for now. Let's see a picture of it. It doesn't give me a picture. Let's go back this here. Think about this piece, right? When we rotate over y-axis, I can't draw here. I'll just go to the whiteboard. Okay, so let's go talk about this. Now we go to the whiteboard. I'll explain. So now let gy be the continuous and negative function. You see this is the inverse function of y equals to x, right? f of x. And I don't want to talk about that. Let's go to the whiteboard for now. Okay, let's think about we have a piece. Let me use the square root of x as an example. Right, my graph looks like this, right? Let's see, this is some other value. I have this region. Right? So I have this region. So this is my R. I can rotate it with over x-axis. I would get this piece, and we already know we use disk method over x-axis, which is pi f of x squared, right? Because the radius is f of x here. So R equals to f of x, right? So radius equal that. But now I want you to think about another situation. So I'm going to use a different color. I can also rotate with y-axis. I won't be able to draw exactly the same. So when I rotate with x-axis, with y-axis, so this is my y-axis, you see what's the intersection? Just use your finger to this, right? When you rotate this way, right? So my section are still circles, but what is my R now? I want you to think for a moment. So for this red piece, for this piece here, what's R? What is the radius now? Okay, think for a moment. Let me see your comments. Paul, 0. Paul, what do you mean 0? Okay, I want f of y. All right, what is f of y? So let's see, I'm using an example. This is square root of x. So this graph is the square root of x. So my f of x equals the square root of x here for this blue piece. So my f of x. Okay. So what's the radius? Do we see what's the radius? This is the radius, right? The radius measured in x-axis. Yes, Damon. The radius is x-axis, but the x keeps changing, right? Over here, x keeps changing, the x value. Let's just pick a point. Let's see from here, right? Let's pick, this drawing is not so good because it's drawn on top. Let's think about this. So radius of the circle it's so difficult to draw. Right? But all I need is this piece. You see, if I draw a red line here, all I need is this. Right? I'm going ahead. I'm hoping I'm not confuse you. I'm going ahead of myself. Right? What's R equals to? Okay, let's do this. So we solve for x. So we want to find the inverse function. We want to represent x in terms of y, right? So we square both sides, we get square root of x squared, which is just x. Then we just get Where the square? Do you see the intersection, the inverse function? How do I write that? -1 of x equals to x squared, right? The inverse function of this. So I'm thinking this is y. All right, this is my y. F of x is my y. Square root of x equals y. So I square both sides. I get an x equals y squared. Would the third object looks like a half sphere? Square root of x, half sphere? No, not really. No, because this is square root of x. You know, my picture is misleading probably. My picture is probably misleading. R equals to negative f of x, y negative. Oh, you mean f inverse, right? So R equals to the inverse function. Yes, the inverse, not negative, but f raised by, so this way. F raised by -1. So inverse function. Yes, the inverse function. Yeah, so that's our R. Okay, this may confuse you a little bit because I'm getting ahead of myself. Let's go back to the textbook. I just don't like the textbook talk about the formula right away. Okay, so this basically is x. Okay, so g of y, basically you think if we have a function f of x, so this inside the R now is the inverse function of f of x. Okay, so it's the x value. But now the changing in x, so we want to find the inverse function of that. So g of y basically is the inverse function of the original function. All right, so that's this one. But then we're cutting along y-axis, right? We're cutting along y-axis. So yeah, ideally we got a picture of this. We didn't. Let's see this example. So the region is defined as this, g of y equals to square root of 4 minus y. This is weird because usually we don't get a function of y. All right, but anyway, let's just follow this. It's saying, all right, we have this graph. We have this g of y equals to square root of 4 minus y. Then what do we want to do? We want to rotate this piece over y-axis, then in the region 0 to 4. So in the region 0 to 4, we want to rotate this piece. We will get a 3D dimension. We'll get this 3D objects. But this method is the same. Just, you know, we're cutting along y from C to D. From C to D, we're cutting along y-axis into infinite many pieces. So we still do pi r squared. Well, let's check what's our r. Our r now would be this x value, right? X value. So that's why they write x value into g of y, because x is changing, because x keeps changing, right? X is this much, x is this much, x is this much, so x keeps changing. So now we're writing x value as a function of y, so which is the inverse of the y. Okay, anyone has any questions over this? So this is rotating the region over y-axis. So the radius now is the x value, but we want to write the x value as the inverse function of the original function. But here we don't have to do that, because here they made it easy. They basically they should give us a function f of x equals to x squared minus 4. You know, x squared minus 4. That's this function. F of x equals to x squared minus 4. But anyway, they solved for us already. right? So in this case, we just set up the integration from c to d. We do pi r squared. Pi is x value. X is written as a function of y, which is just this. You know, we do the calculation. In the end, we get a pi. Yeah, all of us get a pi. Oh, that's different a pi anyway. Okay, let's check this one. So 2.9, I'm going to give a couple minutes to try this one. So this is over, so get a function g of y equals y. Okay, this is easy, identity function, right? So we just get a triangle formed with y-axis. And we will find area from 1 to 4. And the volume rotate over y-axis from the interval 1 to 4. Okay, go ahead, try that. Let me see anyone has comments. If you were to find the volume of that equation over the x-axis, it would be g inverse of y. Yes, that's going to go back to the function. So that function, let me write here, g of y equals to 4 or square root of 4 minus x. Okay. So they're given us already, oh, g 4 minus 1, I'm sorry. G of y equals to square root of 4 minus 1. Right? But normally, we're given a function f of x. Well, of course, sometimes we'll call y, right? Y equals to f of x. In this case, let's say we square both sides. Square both sides. We get x squared. Oh, hold on 1 second. It should be minus. So square both sides. I get a 4 minus y equals to. So square both sides, I get a 4 minus y equals to x squared. So my function is 4 minus x squared. Yeah. So my function is 4 minus x squared. So usually, the question will give us this f of x. F of x. It will say, okay, rotate the piece of region. But this is just a typical example to show us we can rotate the piece over y-axis. Okay, if I change this, it'll be a little bit difficult to find. Okay, the y value is from, so y in which one? Let me go back to see the interval. 0 to 4. 21 pi, 0 to 4. 20 pi, 21 pi. From 1 to 4. Let me try myself. So I get this piece. We want to do from 1 to 4. So this piece. But you know what? These two pieces are the same. So when we rotate, get this. 1, 2, 4. 21 pi. Okay, I just see one person. Maybe that's a typo, right? 20 part, right? Okay, right. Okay, great. Yes. Yeah, that's your typo. 20 pi, 21 pi. Okay. I got a 15 over 2 for 2.9. Right, Jeff? you have to have a pi in it. Okay. Oh, you see your mistake? Okay, great. All right. All right, so you just do pi y square, right? You set up an integral from 1 to 4 dy, you're cutting y-axis. Then your area is just pi r square. What's your r? It's just this y, pi y square. Okay, great. Anyone has any questions? Okay, so why sometimes we want to find over this way? Because sometimes it's easier to find the object, right? The volume of an object. Thinking, putting a rotated y-axis. We will see that in homework. Okay, the second method is called the washer method. Washer method. That's why I couldn't finish the example I did on the whiteboard. Okay. Let's see this one. Will we always be given the function of y? Usually no. Okay. Zachariah, you have to understand the idea of it. Sometimes they give you a function of f of x. And then you see it's convenient, more convenient to think about take the inverse of the function, right? Because it's a revolve over y-axis, you have to get x value, you have to get x as a function in terms of y. So sometimes you need to find, so basically this is the case. Usually we're given f of x equals to da 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 da. And then when we rotate over y-axis, so we need to be able to rewrite x equals to, sum of y, all right? So basically we need to find the inverse function of f. Okay. All right, thank you. Okay, let's see. So we need to learn this method too. It's called washer method. So some solids of revolution have cavities in the middle. So they are not solid all the way to the axis of revolution. If you remember when I did it on the whiteboard, you see the middle is hollowed. So the real object is outside. Sometimes this is just a result of the way of the region revolution is shaped with respect to the axis of revolution. In other cases, cavities arise when the region of revolution is defined as a region between the graphs of two functions. Yes. So a third way this can happen is when the axis of revolution other than the x-axis or y-axis, as I mentioned before. It could be a line, could be revolved with a line parallel to x-axis or parallel to y-axis. Right, so we'll have some other cases to talk about. So in that case, we're going to use a washer method. So let's see this example. When the solid revolution has a cavity in the middle, the slice is used to approximate the volume and not disks. But the washers, for example, consider the region bounded above by the graph of square root of x and below the graph of 1 over the interval 1 to 4. So like this, right? So two functions. We want to find the volume, rotate this region. So just think about the bounded in between of this orange color and this blue color. So the blue color is g, graph of g, constant function 1. And the orange one is square root of x. Now, if we want to find, if we rotate over x-axis, right? When we rotate over x-axis, we see the middle is hollowed. You see the picture on the right? The middle is hollow. The middle is empty, right? The object is this. It's outside shaded. So in this case, we just use a washer method. So what is it? It's the volume of the outside subtract volume of the inside. Right? It's not so difficult, right? So how do we do the volume of outside? Well, we're cutting along x-axis into infinite many pieces. That's our one dimension. The second two dimensions is just the area of this circle. Area of this circle. However, we have to do area of the outside, subtract the area of the inside. Well, just pi r squared minus another another r squared, right? Right. Pi is a common factor, so we just see the outside r, or we could just see this way. You see, just r is, you see the r is different. All right, we have inside the hollow one, the empty one, with the outside solid one. Right, the shape like this, right? Just the middle is hollowed. So just the area, right? We just find the area. The area is just the pi, you know, the outside r, outside radius, which is square root of x, minus the area pi, the inside radius. The inside radius is just 1. Right? The inside radius is just 1 because it's bounded by this function, constant function 1. So this, so the hollow ones is this cylinder. And the rest is just the same. The rest is just the same. So cut x-axis from A to B, for this case from 1 to 4 into infinite many pieces. Right, pi r squared is use the area of the outside circle, subtract the area of the inner circle. So we get the pi times x minus 1. We anti-differentiate that. You get a 9 over 2 pi unit, right? 3-dimension quantity. Okay, anyone has any questions? Just this picture. All right, so let's see this one. The Wash method. Suppose f and g are continuous non-negative functions such that f of x greater than g of x, which means f is outside, g is inside. Okay, Ali is asking a question. Isn't the square root of x for the whole thing, including the empty space? Yes, of course. Of course. That's why we subtract. Yeah, square root of x is the whole thing. The radius is from x-axis up to the orange one, right? So we find the volume of this outside, subtracting the volume of the inside. You're exactly right. Yeah. So basically, we have outside f of x, the outside, g of x is inside. We just have pi of the outside radius, f of x squared, minus inside radius, which is g of x squared. Okay. Let's see this example. Find the volume of solid of revolution formed by revolving the region bounded above the graph of f of x equals x, identity function, and below the graph g of x equals 1 over x, over the interval 1 to 4, around the x-axis. So a lot of times the question itself doesn't provide the graph, so we should be able to draw the graph. So 1 over x, right, the orange color, because the interval is from 1 to 4, so we don't have to care about the other branch. And the identity function just cut the first quadrant into half. So from 1 to 4, from 1 to 4, from 1 to 4. So okay. So we see this hollowed one is the dotted orange color, right? So that part is just hollowed. So we just, you know, apply the formula. So cutting along x-axis into infinite many pieces, we do pi, the outside r square, subtract the inside r square. So f square, right? F square, the top one or the outside one, subtract the inner one, g of x. So we'll get x squared minus 1 over x squared. anti-differentiate that, we get a number. Okay, anyone has any questions? Okay, so the difference between disk method and the washer method, the disk method is a solid. There's no hollow middle. The washer method just we have the subtract the hollow volume. That's it. So basically, you know, we find the volume of the outside one, subtract the volume of the inner one. That's it. Right? Even we're writing this way, right? Okay, 2.0. Give you, let's see. Yeah, we have time. So I'll give you 5 minutes to try this 2.1. One, two, three. Okay. All right, let's see if we have the same answer. Okay. Golam, I agree with you. And Shahaya, yes. Okay. Relevant. So you don't need to do the approximation to 3.33 because 10 divided by 3, yes, it is indeed a 3.33. But to keep as 10 over 3 pi or 10 pi over 3. All right, great. Okay, what about the rest of you? Alejandra, Alexander, Alexis, Kelly, because I don't see you. All right. Okay, anyone has any questions? Just want to make sure everyone gets the idea of it. Still working on it. That's fine. That's fine. Okay, anyone has any questions? All right. Okay, if you don't ask questions, I'm just assuming you know what to do, okay? If you have any questions, feel free to stop me anytime. Okay, great. Okay, we all got 10 over 3 pi. All right. Okay, now, of course, we can rotate the piece of region over y-axis. Right. Okay, all right, Alexander. The idea is the same. Now, just, I really wish that I have a picture. Okay, anyway. So just picture in your head, all right? We're revolving this piece over y-axis now, over y-axis, right? So then the radius will be the x value. So the x, where do we get the x value? We find the inverse function of f. So f inverse of x, the inverse function. Because x keeps changing now when we cut along y-axis. So we just find the inverse function of f, and that's our radius. And of course, we always do the outside, right? Outside volume minus the inside volume. So the radius of outside, they use u of y to represent. The v of y that represents the inner radius. Let's see this example. So we want to find the volume formed by this one. Above f of x, 4 minus x, and below the x-axis. I think they did it again. It's below 4 minus x and above x-axis. So over the interval 0 to 4. Okay, now you see, okay, now it's around the line y equals -2, right? It's not rotating over x-axis or over y-axis anymore. So this is rotating with a line with -2, which is parallel to x-axis. So the radius is still the function value, but we need to subtract the hollow volume. So 4 minus x is this line, right? Y equals to -2 is this line, the blue line. So 0 to 4. So the region is above x-axis and below f of x from 0 to 4 is this shaded part, the shaded region, which is this isosceles triangle, right? Isosceles triangle. So now we want to rotate this piece over y equals -2. So the line of symmetry is y equals -2. It's not over x-axis anymore. So now we see we have to use washer method, right? Because over x-axis, we will use disk method. We don't need to subtract anything because the solid piece is solid, no hollow. But now we want to rotate over y equals -2. We see in between x-axis and y equals -2, this is hollow, right? So when we rotate, we get this, but the inside is hollow, right? Inside is hollow from 0 to -4 on y-axis. It just doesn't show much here, but there's a hollow piece. Wait, how is that around the y-axis? Oh, hold on a second. Are we talking about around y-axis? No, we're not talking about around y-axis. Sorry, we shifted Ali. Okay, sorry, I didn't make this clear. Oh, the washer method. Sometimes we use, so this one we use for rotating x-axis because we have this, because the hollow piece is here under this, right? Another one, we're still rotating with x-axis. We shifted our content. We're not talking about over y-axis anymore. We finished talking about rotating over y-axis. We're coming back to talking about washer method. What's another way to use washer method? Well, some other situations we use washer method. It could be around x-axis, it could be rotating over y-axis. Now we're coming back to axis now. Okay, we're coming back to axis, rotate over x-axis now. So we have this region, so this isosceles triangle over here, right, which is formed by f of x equals to 4 minus x and the x-axis. So this shaded region, we're rotating this piece not over x-axis. If we rotate over x-axis, we just use disk method. Right? We're not rotating that, we're rotating over y equals to -2. We're rotating over this line, y equals to -2. So y equals to -2 is a line of symmetry. Okay, so when we rotate, right, from 0 to -4, so this the y value. So y value, look at the y-axis. Okay, from 0 to 4, the inside is a cylinder, right? It's a cylinder. So that's the hollow part of this object. So this 3D object is a solid above x-axis and below y equals to -4. But in between of 0 and -4, the inside is hollow. The inside is hollow. So that's why we need to subtract. We need to use Washer method, which is we find the volume of the outside, right? Subtract the volume of this cylinder inside. So what's the volume of outside? We're cutting from 0 to 4, right? X-axis. So we integration from 0 to 4 and dx. And our integrand is the area of this circle. What's the area of this circle? The outside one. So do we see that? So this line is f of x equals, let me see, I can type in the chat. So we need to figure out r, right? Outside r. Let me use big R to represent the outside r, okay? So we need to figure out the outside r and the inner r. So what's the outside r? Outside r equals to x minus 2. So the function value, f of x, right? Let me use f of x first. F of x, do you see anything else? 6. 6 is the end of it. So I'm talking about in general, the f of x value. So 6, you see, it's from 0 to 4 plus 0 to -2. That's 6. That's great. Okay. So how do I, starting from 4 to 6, I'm adding 2 to my radius, right? So the big R, so outside R, is just f of x plus 2. Does that make sense? Okay. Now let's figure out the inside R. I use a small r. You see that's just 2? Hope that makes sense for you guys. Okay. So now we just do pi, big R squares, we have pi. So our integrand is big pi r squared minus little r squared. Okay, let's go back to the, so anyone has any questions? You just have to be able to see the inner cylinder is a hollow of this object, is a hollow part of this object. So outside radius is just a function plus 2, right? Which is 4 minus x plus 2, we get 6 minus x. And the inner one is just 2, the radius is just 2. So 6 minus x squared minus 2 squared. You know, we do the calculation, right? We anti-differentiate. So in the end, we get 160 divided by 3 pi. So when we rotate it over x-axis, rotate it over y-axis, rotate it over any other line, you know, the answer will always have pi in it. Okay, anyone has any questions? So it's this picture basically. Because you see from 0 to -2, then that's not the part of the region, so we need to subtract. Okay, no questions, we'll keep going. All right, your turn. So now f of x is x plus 2. Okay, so bounded below this function and above x-axis over the interval 2, 3, around the line y equals -3. Okay, and y equals -1. Draw the picture, help you to see it. So I'm going to draw the picture myself too. from 0 to 3. A good number. Okay. I'm hoping to see everyone's answer. So today we learned the disk method, washer method. Both methods are related. Yeah, Golem, I got the same thing. All right, yeah. Yes, Shahaya. Okay, same. All right, let's wait a little bit. Let's wait a little bit. Let me take a attendance. Let me take a picture of the attendance. Okay. Yeah, 60 pi. I got a 60 pi also. Let's see the rest of you if you get the same thing. Yes, 60 pi. Yes, okay. All right. Anyone has any questions? So Nuzat, N-U-Z-H-A-T. I didn't see you typing anything yet. And also Kelly, Fujun. Okay. Okay. Oh, it's hard for you to type in the chat? You only type your answer. I don't need you to show me steps. Oh, okay. All right. So I'm just hoping everyone understands what's going on. Anyone has any questions? Okay. All right. No problem, Kelly. All right. Let's. Okay. All right. All right. Good. All right. Thank you. All right. So I'm going to assign you some homework now. 25. We still have some time. Okay. Let's see. Cylinder shells. So calculate the volume of a solid of revolving by using method of cylindrical shells. Compare the different methods for calculating volume for revolution. Okay, cylindrical shells, right? So this is a cylinder outside. So outside the cylinder. So again, we're working with the solid of revolution. As before, we define a region R bounded above by the graph F and below by x-axis. Okay, this is type O everywhere anyway. So it's supposed to be below f of x and above x-axis. And on the left and the right by the lines x equals A, x equals B, respectively, as shown in here. Right, we're rotating this piece over x-axis or over y-axis. This is rotating over y-axis, so we get this cylindrical picture. So this is different from what we have done before. Previously, regions defined in terms of function of x were revolved around x-axis or line parallel to it. So now we're revolving this piece over y-axis, and sometimes we can revolve this piece over y-x equals to something else, so which means a vertical line parallel to y-axis. So when we could think about like this, we could think about the area. It's not a circle anymore. And the area is just, how to say it? Think of this piece as a roll of toilet paper. Okay, think as a roll of toilet paper. But each piece is thicker than toilet paper. So each it's just like this, right? Think about like a toilet paper. And yeah. Then think about it. So a way to find, actually let me use this. Think in my hand I have a roll of toilet, right? A solid. I want to find the volume of that. So what I could do, I could slice, right? I could cut through, and then it becomes, so the toilet paper, I cut right in the middle. Think about this is the all those center are solid. I could, from the middle point, I can cut through. Then it becomes a piles of what? Piles of rectangles, right? Just imagine that. Then I can find each area of the rectangle, then add them up. So that's another way of seeing this. So it's called a shell method. Okay, S-H-E-L-L, shell method. So basically, look at an object, we just cut through from the middle, cut through, then we lay them out. Then each intersection is a piece of rectangle. Then we just find area of that rectangle, we add them up. So that's the idea of shell method. Exactly, but Zachary is saying like a bunch of rolled up rectangles. You're exactly right. Right, you're exactly right. Okay, but sometimes this method confuses people. But once you get this idea, you follow this idea, you know, find volume for any object, we need 3-dimension, right? It's a 3-dimension quantity. 3-dimension quantity. In this case, we know we have a pile of, you know, a cut through, we have a pile of rectangles. So what do we have to do? We will have to find the length, width, and height. That's it. And we follow the idea. Okay, so right, so we can look through this angle, right? We will have this dx So one quantity is the delta x, right? Another quantity, of course, is f of delta x, right? So the volume of the shell equals to one dimension, you know, at a certain point, x star represents at a certain value of x, a chosen one, right? So that would be the height of this piece, right? So one dimension of the rectangle. Then times the difference of the area, right? The difference of the area. So for this one, yeah, maybe we can, this is not a good, this is not a good picture because this is seems like a solid, the middle is solid. But if we could imagine, we rotate this piece over some other vertical lines instead of y-axis, right? Okay, so idea comes from here, then we simplify. So let's see xi minus 1. So in this case, we see, so this value is xi minus 1, and this one is xi, delta x, right? Changing x is just xi minus 1. So we want to find pi r square of this, pi r square this. So this is our r, this is our r. Right, so we have pi xi squared minus pi xi minus 1 squared and multiplied by the third dimension, right? The third dimension. And from there, we can simplify this. So we simplify because they're related. In the end, what do we get? We get something beautiful. We get a 2 pi f of x, you know, at the chosen point and those values, right? So if we change xi minus 1 delta x, so what we have shell volume equals 2 pi f at the chosen point. And that's a beautiful thing. What is that? Do you recognize that is the circumference of a circle, right? Think about the f of x star is r, right? We get 2 pi r. Circumference of the circle. Circumference of the circle. When we cut, how do we find the length of the rectangle? So when we cut the circle, right? The circle, we laid it out. The circumference of the circle becomes the length of the rectangle. So that's the picture. So we have this 2 pi r, okay, f x star. Then we have those two quantities. Well, xi plus xi minus 1 divided by 2 and the delta x. Well, delta x is the difference from xi to xi minus 1. Xi plus xi minus 1 over 2 is the choosing point, right? If we choose this x star as middle point of those two, right? At the middle point of those two. So we get this. So the shell volume is about 2 pi, the function value at the chosen point, times the chosen point, and times the difference in x, right? You could think if we cut along x-axis, so this delta x is just dx. So picture is this, okay? We cut the cylindrical object, right? We cut from the middle, so we get a pi of rectangles. And what's the length of the rectangle? We want to find the area of the rectangle. We want to find the volume of the rectangle. Rectangular prism, let's put that way. So just think about a thicker, each piece is thicker than the toilet paper, maybe like a rubber, you know, a piece of rectangle rubber with a third dimension. So we're going to just add up all those volumes of this rectangle prism. So what's the length? The length is 2 pi r. The length is just the circumference of this circle, right? And the width is just a function value. The width is just function value. So the width is a function value. The length is the circumference of this circle. And then the height is the difference of x. The height is the difference of x, right? Delta x here. Okay, so I have this. You know, we keep going, keep going, keep going. In the end, we get this beautiful formula. So we're cutting along x-axis from A to B. We have 2 pi x. This is cutting along x, right? We have 2 pi x. That's the circumference of the circle times f of x. F of x is the height, right? The height of the cylinder now becomes the width of the rectangular piece. So 2 pi x f of x dx. Right. So this is called shell method, but this is a shell method. Okay, now let's see this one. Rule the method of cylindrical shells. Let f of x be continuous and non-negative. Define the region as bounded below the graph f, above x-axis, on the left by the line A, and on the red line by the B. Then the volume of the solid revolution formed by revolving R around the y-axis, is given by, from A to B, set up an integration from A to B, cutting along x-axis. So 2 pi x, remember? 2 pi x is the length of the rectangle, but the circumference of the circle, right? Multiplied by height, multiplied by the height of a cylinder, which is the width of the rectangle, right? Then multiply by dx. So we have length times width times the third dimension dx. Okay, anyone has any questions? Usually people get confused with shell method, but if you follow this, if you really understand this picture, so everything is hidden in this picture. If you understand this picture. Okay. Okay, let's see an example. So the region is below the function 1 over x, above x-axis. The interval is 1 to 3, and we want to find a volume revolved with y-axis. So we have this piece. Under 1 over x, above x-axis, from 1 to 3, we get this region. And when we revolve with y-axis, so we get this hollowed. And of course, we can use disk method. We can use washer method, right? You can use washer method for this, but let's try to use shell method, right? Shell method, remember what do? We cut through this, right? We cut through this, then we lay them out. We have a pile of rectangles, so we evaluate the area of every rectangle. So we have 2 pi x f of x. Right? 2 pi x, what's f of x? F of x is just 1 over x. Well, x times 1 over x. The integral is just constant, 2 pi. So evaluate, we get 4 pi. Anyone has any questions? So if we understand the picture, we understand in this method, shell method. So, right, the formula is 2 pi x f of x for the integral. Watch, let's try this one. So we have a couple minutes. We probably we don't have time for this. Let's do this one. Let's see the, because this is the method of cylindrical shells 2. Let's see this one. So define R as a region below graph 2x minus x squared, where it's downward parabola, and above x-axis over the interval 0 to 2. Find the volume of the solid revolved by y-axis. So I have this piece of region, right, below the downward parabola, above x-axis. Now we're revolving this one over y-axis. So we see the middle one is hollow. So we have 2 pi x f of x. So 2 pi x f of x is 2x minus x squared. Right? Let me do the calculation. Get the 8 pi over 3. I don't know why they call the method 2 a shell. Oh, example 2, I guess. Example 2. Okay, anyone has any questions for this? All right, keep going. Okay, now revolve over x-axis. Okay. We don't see, okay, they don't show a picture. But it's very similar to y-axis, right? It's just the x, just now the circumference is different. The r wouldn't be x, but the r is f of x now. So we get 2 pi y, we're cutting along y-axis. So we have dy from c to d, dy. And the radius, so we have 2 pi y, because the radius y now is a function value, f of x. And then what's the height? The height is the inverse function of f of x, which is g of y. You can think as x, or f of inverse of x, the inverse function. Or if you want to, you can understand everything in terms of y, because this is perfect symmetry with the other one, with the other formula. So this formula is with x-axis. Right? You see we have 2 pi x, we're cutting along x-axis, we have 2 pi x f of x. Right? And here, we have 2 pi y, g of y. Well, what's g of y? F inverse of x, right? The inverse function of f of x. We're cutting along y-axis. So this is perfect symmetry with cutting along x-axis. Let's see an example. So here we have this g of y, or here we don't have to do much because we're not given f of x. They already solved for us. So the inverse function. So 2 square root of y, and from 0 to 4, and rotate it over x-axis. So just plug in the formula. Right? The picture is this. The picture is this. We want to rotate this piece over x-axis, so we get this one. But you see this inside is hollow. Right? So shell method is shell method. If we could use shell method, we can always use washer method. Okay, you may try both, you know, to just master this skill. So we have 2 pi y, g of y, dy. What g of y is given? Sometimes we'll have to solve for g of y. In this case, is given. You know, which is an anti-differentiate from there. All right. Anyone has any questions? Okay, so great. So today we learned disk method, which we mentioned last time, and then mainly we learned washer method and the shell method. All right. So shell method, I know, according to my experience, sometimes students get confused with the shell method. The shell method is understand the one picture. Okay, cutting a roll of toilet paper, lay them out as rectangles. Then find the volume of each rectangle, then add them up. That's the idea. Okay, I will post the homework on Blackboard and also on my Open Math. All right. I hope you can follow the due date to finish your homework. So, all right. Anyone has any questions? Wait, Professor, how many midterms? How many? Just one. We have one midterm, one final, 2 exams. 2 exams, 1 midterm, 1 final. Right, I announced the midterm. So just for everyone to be alert and prepared. Do we only submit 10 questions for each homework assignments? Yes, Zenith, but hopefully you finish everything. You pick up the 10 of the best answers. You know, the 10 questions you feel like you have no doubts, you did it right, and send to me. Yes, two tests in total, 2 exams in total. You're right. Are we being graded? No, homework is by completion. It's not by you did it wrong or right. It's different. So grading homework is different from grading exams. Grading homework is by your completion. You complete on time. You complete the 10 questions. You complete on time before due date. I mean. Yes, Bishan. Yeah, homework 4. Choose 10. Do every question. Choose best 4 and send to me. You don't give extra credit? Not at this moment. Just try your best to, to do your homework. If you have extra energy, do more. All right? No extra credit. Okay, have a good night. I haven't checked yet. James, if you send to me, you check your sent folder. If your sent folder recorded, that means that you have sent to me. Just make sure my email is right. Okay, thank you. Have a good night. Let me stop recording.